In this exercise, we'll take a look at several vector fields and determine if the divergence of the vector field would be positive, negative, or zero. And we'll assume the vector field looks the same in all horizontal planes. The divergence of a vector field measures the rate change inward or outward of a vector field and is also called sync. For a velocity vector field, this would represent the rate of flow inward or outward from a given point. If the divergence is positive, the rate of change is outward, like a heated gas that is expanding. If the divergence is negative, the rate of change is inward, like a cooled gas that is being compressed. If the divergence is zero, the change is not inward or outward, and we say the vector field is incompressible. So looking at our first example, to help visualize this, let's sketch a balloon or circle in the vector field and see if the rate of change is inward or outward, or if the flow rate would be inward or outward. So if we sketch a balloon or circle, let's say here, I think it's pretty easy to see that the flow rate would be outward in all directions, which means the divergence of the vector field is positive. Notice how in this case I drew the circle or balloon at the origin, but this does not have to be the case. We can draw the balloon or circle anywhere. Let's sketch it somewhere else. Let's say we sketched it here instead. Notice how we have a large flow rate outward here, but notice how we also have a small flow rate in here, but because the flow rate out is larger than the flow rate in, the divergence is still positive. Looking at our next example, let's go ahead and sketch a circle or balloon here at the origin. And it's pretty easy to see in this case the flow rate in all directions is inward, which means the divergence is negative. Let's also move the circle, though, to a different location. Let's say we sketch it here this time. Notice how we have a large flow rate in from this direction, and we have a small flow rate out in this direction. Because the flow rate in is larger than the flow rate out, again, the divergence is negative. Looking at our next example, again, let's go ahead and sketch a circle or balloon inside the vector field, let's say here. Notice on the left we have a flow rate in. On the right we have the same flow rate out, which means the rate of change is not inward or outward, and therefore the divergence is zero. Wherever we sketch this balloon or circle, the net flow rate will be zero, and therefore the divergence is zero. Let's look at one more example that's a little bit more involved. Again, to help visualize this, let's go ahead and sketch a circle. Let's go ahead and sketch it at the origin here. Notice how we have a flow rate in from this direction, and we have a flow rate out in this direction, but the flow rate out is less than the flow rate in, and therefore the divergence of the vector field is negative. This would be true for any point or any location in this vector field. I hope you found this helpful.